Hello everyone, welcome back to a new episode of EXAPUNKS. As I said I would in the last episode, I started off-camera implementing the solution that we sketched out in the previous episode for this brain interface tree exploration. And it's not done yet, but I've made a lot of progress, and I wanted to share with you guys what I have so far and some interesting snags I ran into along the way. So recall that the idea is to treat this as a tree, right? We noticed a long time ago that most of the networks we traverse are shaped like trees, where -1 is go back to the root. In this case, -1 isn't go back to the root, it's like just you have to figure out what the path back to the root is, but there is a path, right? It's a tree, there's no cycles, there's no nodes with two parents, and so on. And so the algorithm was to just basically do a depth first traversal, but figuring out how to do that with these operators is a little bit tricky. So the idea is to use a file that we carry with us as the stack of, if you've written a computer program that traverses nodes in a tree in like a normal programming language, you typically have like the language itself or the runtime or whatever keeps track of a call stack for you, the list of like what functions you're in the middle of. When you return from this function, where do you go? We don't have that here because we don't have functions, but the file that we're going to create is analogous to our list of return addresses, where the address is actually just a single link. But normally, in a modern language, the call stack also has like all the local variables you were using in that function, right? We don't have that. We just have a couple registers, so we have to figure out how to save those. And the thing that I realized is so when we enter a node, first thing we do is we fork off a couple copies. One copy is to broadcast the nerve address, or the data from the nerve if there is one. We also fork off a copy to broadcast the to basically like three things we'd like to push onto the stack, but we can't push them like all at once. Where the three directions that we still need to explore and aren't the direction we just came in from. So we're sort of using this SR1 guy. No, SR0, he's our director. Using him to store what you might call local variables. The only local we need here is a list of like the directions left to explore. And in particular, which direction not to explore. So he's got a pretty simple macro here, right? We put the direction we don't want to go into X before we REPL to this guy, and he just like 4 times checks the 4 different directions, and if any one of them is equal to X, he doesn't broadcast it, otherwise he does, and then when he gets to the end, he halts. This macro was easy enough to write, excuse me, and didn't actually have to even test. Like, obviously, I was testing things, but this one didn't need to be rewritten at all. So it looks a little complicated with all these add signs, but really it's quite simple. And so the idea is we have, I think I mentioned, a few states. The first time we enter a node, we're in a state we call enter. You can also view this as kind of like a state machine, right? With some externalized memory. It's sort of a push-down automata, I guess, because we have access to a stack, right? But when we're in the enter state, we set up all the like stuff to help us track how to explore this node, and we only enter this state once per node in the graph. It's important we don't re-enter it ever, because then we would start exploring in an infinite loop. We would send someone to 3, and then later we'd get back here and say, oh, I've entered this node for the first time, better send someone to 3. And that would be a loop, so we don't want that. And so a thing that I got wrong a couple of times was actually managing the file pointer, like where we are in the file. because I kept forgetting that like when you drop a file and pick it up, your file pointer is reset. And so I was testing, I was watching, like, yeah, wow, they're exploring, they got all the way down to here, that's amazing. And then they went back up, oh my gosh, the stack is working, I said to myself. And then they went here, oh my gosh, the local variables are working. And then it returned here, and I was like, it's amazing. And then it exploded, because there was actually only one entry on the stack. Instead of pushing onto the stack, we had just been overwriting the one value that was on the stack, because we kept dropping the file, picking it back up again, right? So I had to add in a few seek 9-9s to get back to the end of the file, the only end we ever look at. And it's kind of a bummer. I need a couple of no-ops here when we first enter the node, because it takes some time for the replicating, the guy who's giving directions, acting like our local variables. This one. It takes him a little while to like broadcast the first value on M. And it's not that long unless the link you traversed is the first one he's thinking of sending. And then he has to like say, oh, no, not that one, the next one. And so if we have fewer no-ops here, then we actually test for message ready before the guy is ready to send a message, and we end up missing one. So anyway, the idea is we enter, and so the link that we just traversed is in X when we enter a node. Copy 1 to X is how we start. We pretend that this link 800 is actually link 1. And then when we enter a node, we say, ah, I lived. This link must actually exist. Therefore, negate X and then fork off these two guys. And then add the negated version of X to the end of our stack. Great. Then we enter this searching loop, where we want to follow the 3 directions being broadcast by the local director. If there is no message left, then we jump to return, which is where we say, I guess I must be done exploring this node and all of its children. Therefore, I must go back up to its parent. And we'll look at what that does later, but first let's continue reading through search. In search, if there was a message ready, we copy it to X, and we replicate a new exa to stay behind in case we explode when we try to traverse the link in X. And then we link to X, taking the file with us, of course, hopefully. If that succeeds, then we'll still be alive and we'll jump to enter. We'll be in some new node and we want to explore it again, and so then this recursively works. What about the guy who stayed behind? His job is to do nothing, wait for us to die, and then he picks up the file that we might have left behind when we died, right? If we tried to traverse a link that didn't exist, we'll have left the file behind. He needs to pick it up and take over the job. And he jumps back to just search, not to enter, because he's continuing to explore an already explored node. The direct guy was easy. Return is pretty simple too. We know we're carrying the file, either because we're coming back already from some other node, or because we just picked it up from some idiot who dropped it. And we tested to see if there were more nodes to explore, and there weren't any, so we're going to go look at the end of the file, seek -1 to point to the last value in it. And importantly here, test whether we're at the end of the file. Because if so, there are no more nodes, no more backlinks to traverse. We must be back at the root. And if so, we jump to done. Done is what we do when we get to the root. I currently have this sort of stubbed out. It's incorrect. I have it just implemented to kill the guy who's been up here adding numbers. That's clearly not what I want, but I just wanted some way to notice that I'd handled the end condition correctly. Otherwise, we must not have been at the end of file, and so we link over the value stored in F to go back 1 level. And then we erase that value from the file by seeking back over it and voiding it. and we jump back to search. We don't jump to return because we just know we want to go back one level. There might be more exploring left to do at that level. So we have to check and see, is there a message for us? And that's what search does. From search, we may very well jump straight back to return. Okay, and also there's like, there's this guy here who just is copying all the nerve values and dumping them into a file. This will not be the actual final implementation of the master. We're probably going to do some kind of online sort, like insertion sort. Blech. But this is enough to know that I'm doing things reasonably well. So let's watch it go for a little while and see how they're kind of following what you might call a left-hand rule. At every node, they fork off a thing, and yeah, indeed, we get back to the root and everyone's dead. So if you watch more slowly, you can see there's some excitement in each room before something interesting happens. X's winking in and out of existence as they try to explore nodes that don't exist. And you can sort of watch the progress as well. You can see visually what kind of state there is, because every node that has an X still in it is one we still need to explore some children of. So we know that when we return from here, we're going to get to here, and we know we won't go back because there's more exploring to do from this guy, wherever that is, as it happens here. Likewise, when we get here, we won't go straight back. We'll explore something else, apparently this way. Right, and so you can tell some of what's going on just by watching. And here it's a dead end, so they do a bunch of copying before they go back. But they handle it pretty well, right? And it looks very purposeful even, right? A lot of pointless copying, or a duplicating of X's. Not pointless, but it looks sort of pointless unless you know why they're doing it, right? It turns out to have been useless, but the reason was there might have been a link here, and we need to survive that possibility. And then we get back to the root, and everything is as we wanted. I guess the most obvious thing to do in done is wipe the file you were carrying. It's now empty and useless. Although, I think you can afford to... You can leave it in the host, so maybe I don't need to do that. Create a file. Okay. So now we have to implement sorting of a file as we receive values. And I'm not going to do that on camera either. That is not... It's a simpler algorithm than what we figured out here, I think. But implementing it will still take a while. Because it's such a pain in the butt to insert values into the middle of a file here, because you kind of have to insert them from the back, and you have to copy stuff as you're going. It's the worst. Yeah, so I'm not gonna do that on camera either. I'll just I'll come back and show you guys when it's done, and then we'll have hopefully won the game. All right, see you guys in a bit. All right, I'm back. So I have in fact implemented the sort routine function code. It didn't take as long as I thought it would. It would have taken longer if I had to be explaining myself every line that I wrote, but still, maybe you could squeeze it into the last video. Who knows? I had to make a couple of changes to the code you guys already saw to account for some things that I realized. The tree traversal stuff was all still fine, but the protocols I was using to communicate back to the guy working on the file needed a slight tweak. Because I noticed something kind of odd. Well, two things. It says actually sorted as pairs from lowest to highest host name, which I didn't read this very carefully the first time. Since when can you sort keywords? Host names I thought were these opaque atomic objects that just you can't do anything with except test whether they're equal to something. But no, apparently you can compare them for greater than, less than, just comparisons, I guess. And so we're actually supposed to sort not by nerve value, which is like being a number, the obvious thing to sort, but by hostname. And furthermore, I looked at the solution here, and it has the host names first. I didn't think to check that when I first implemented it. Which is a bit tricky, because you don't actually want to transmit the host name first, because there will be many hosts with no nerve. You want to try to transmit the nerve and then die, if there wasn't one, so that you don't transmit some useless host name. So I had to swap things a bit here. I had to have, rather than just copying M into F, I had to copy it into X, and then copy M to F and copy X to F, reversing the order of the two objects. Fine. Now, I actually gave up my dream of doing an online sort, of like sorting values as they come in, which I think would have been pretty cool and could have been done. So like, I think insertion sort would be better here, because the value is being built, the list is being built as you go. And so like, if you sort it in parallel as you receive values, like that should be faster than waiting for all of them and then sorting them all, right? But I couldn't actually work out a way to do this, because you never know when it's safe to interrupt the guy who holds the file. He might be in the middle of a sort. So you can't just kill him to say, I'm done, let's go home. And he doesn't know he's done, because there might be more values out here. And he never knows how long it's going to take to get the next one. So that's no good. So I ended up having to just say, well, too bad. I guess we'll have to copy the whole file and then interrupt the file guy by killing him when we have returned to the root with and therefore know we have all the values. And then we'll just have to sort the entire list in place all at once. What a bummer. So that means bubble sort it is. Basically, I changed this from done to sort because this guy is not actually done anymore. He's now the sorter. So we jumped to sort out of return instead of done or die or whatever I called it. And so bubble sort is a pretty simple algorithm, and it's quite inefficient if you have like fast random access to things. So it's not typically used. But here we don't have that. And we don't have much memory to work with, so it's simpler to just do a bubble sort because it's very local. It works on like one subsection of the list at once. So the algorithm is basically start at the beginning of the list and search forward looking at pairs of adjacent elements until you find a pair that is in the wrong order. That is, say, if like the larger one is first, which is not what we want. If you find such an element, such a pair of elements, swap them and go back to the start of the array and start over. And eventually, you'll have made enough swaps. Like, the array gradually tends towards sortedness in this way, right? The smallest element will eventually propagate towards the beginning by being swapped with everything else. And other elements will propagate back to the beginning, except they won't go past the smallest element. And if the smallest element isn't there yet, then when you do go into the smallest element, it goes in front of those other values, so it's all fine. So to implement this with x's is a little bit like annoying. In particular, the swap function. There were two ways I could have done this, and I don't really have strong feelings about what is better. So you need 4 values. Like, you need to do a pairwise swap of like both the host name and the nerve value. You need to have 4 values to work with to copy around, right? And there's only space for 2 in an exa. So what I did is I just used the file itself as like the backing store. I make sure I only need 2 values at once. I determined that I should do a swap. I swapped the host names by copying them into X and T and then writing them to the right places. And then I read both of the nerve values and then I swap both of those. Alternatively, you could You could copy... Actually... Yeah, you could read the... You could copy some two values, not clear exactly which two would be best, and then replicate a new exa holding them, and have him like save them and broadcast them back to you when you need them. And then you'd have to do less seeking around in the file. As you can see, this part, the swap, is actually more complicated than the search. But this was simple enough. You just like... You already have one value in X, and you're pointing at the other one, so you might as well copy it to T. And then... we just do a couple of seeks to, like, erase them, to swap them. I'm not sure exactly what you would use... What would be the best way to use the second exa? What two values would you want him to hold? Like, ideally, you would send him a chunk of two things at a time. Let's say the first and second... The first pair's host name and nerve value. But you're kind of... Well, yeah, maybe we can go back and change that. But, okay, so this... Anyway. So the swap algorithm is pretty simple. And if you ever get to the end of the file without running into any pairs that were in the wrong order, then you must be done. Great. And so we just jump to die if we run into an end of file. So on the whole, actually, a pretty simple sort. A bit of a pain, but simple. And it is slow as molasses. You thought watching them traverse this stuff was slow. Just wait until he starts sorting this file. Here we go. And he just spends forever on the first few values, and then, like, I mean, bubble sort is not a fast algorithm, unless the list is already sorted, and then it's excellent. But you can see he's sort of like, you know, the values are getting to be in the right place. Low ones are kind of close to the front, more or less. And he generally skips over the first values. Like, as far as he seeks, that's like, oh, the array must be sorted up to there. And then he, like, finds a new value and it's like, oh, geez, this one's got to go all the way back to the beginning. Are you kidding me? And, like, he spends a long time doing all those swaps. So, oh, thank goodness. They really speed things up for this. So, poor on cycles, which is interesting to me. Great on size, and good on activity, although it's not too surprising. We're actually in the top 10th percentile on size. Cool. So I was confused about the... Let's go back to editing. I was confused about this like hostname comparing thing, and so I ended up looking on Reddit to see like if people had discussed like, why does it say hostname? Is it just confusing? And I wanted to see what other people had done for the tree traversal algorithm once I had implemented my own. I don't know if I saw anyone who did it quite the way I did. There were a couple of people who figured out depth first search is the way to do it, and they still did it differently than I did, and it wasn't totally obvious, all of them. But there are a lot of people who just, like, use the random, like, replicate in every direction all at once, spam nodes everywhere, and if you find a nerve, then, like, hang on for dear life. And they, like, they had some... I couldn't totally figure out their, like, coordination algorithms to make sure that they don't step on anybody. There were some people who did the kind of like catch and repeat thing I was talking about, like if you try to, I don't know, where some exas accidentally grab someone else's value and then like they have this, oops, there must be congestion, let's back off. He mentioned that it's sensitive to the size of the network, which makes me think he didn't figure out exponential backoff as the solution to that. But anyway, why was I talking about this? I don't know. It was just interesting, the number, and there were a lot of people who did that, and then like the nodes didn't really know when they were done, and so like after exploring the network and doing all the sorting, they had to again traverse the entire network with a swarm of killer robots killing all the leftovers, which seems very untidy to me. And they were running into size trouble. Like, I have a correct algorithm, but I cannot write it because it's too long. All right, we can get rid of some of these white spaces. I guess it doesn't matter, right? Yeah, I don't know. I kind of like them because they remind me that, like, they're separate sections of the code versus, like, a label that's used within a section for jumping to something. All right, so we wanted to try, let's call this file storage. And I wanted to try also calling the, using EXAStorage to make the sort a bit simpler. So when we want to swap, what exactly do we need to do? First of all, I probably want this seek minus... I don't... Do I want the seek minus 1? I guess. No. Let's put this here. Only if we have not gone to swap, we'll seek minus 1 so we can continue searching for values. In the swap case, we are currently pointing at the second nerve, and we have the first host name in memory, which is not useful. So let's seek minus 2 to get us pointing at the first nerve value. Copy that into T. And now, when we replicate a new EXA, he's holding all the values we need from the first host, right? REPL to repeat. We'll call him a parrot. There we go. Mark parrot as whatever. He already has the 2 values we need. So we have, okay. And now we need to copy f into x, copy f into t. Now we're holding, instead of the first 2 values, we're holding the second 2 values. We can seek minus 4? Yeah, 4. To point to the beginning of the first value guy, which is what we want to overwrite. And copy x to f, copy f to t. And then we're pointing at the second set, right? So we can copy m to x, copy m to x. Right? And this guy's job is just copy x to m, copy t to m, and then halt. So let's see how this looks. Does it even work? So we're ready to replicate, and we have AR 90 and like a minus 37. We have this stuff in, and that's what we've given to our clone. He has those things. So we want to read the other things, which we have done. Go back and write them over the originals. And then that doesn't seem right. Shouldn't it have been this that we wrote? Okay, first of all, I wrote X when I meant F. And also, copy F to T? What am I doing? Copy T to F, maybe? Yeah. So here we are, and we now have, we want to copy these 2 values into here. And we copy the other values from this guy, and great, we effected a swap. And this guy has halted. So this should still be correct. And the interesting question is, did we improve or make our metrics worse? Ugh, it's like you can't, since it's a new solution, it won't show me what previously was. But we're at 26, 87, and 91. Activity should be the same, so I'm not too worried about it. 26, 87, and 91. Oh, she's talking. I can't go. I wanted to look at. Alright, well, we'll listen to this. We're set. It's a good thing I released the phage, isn't it? This whole time you thought it was a curse, when in fact it turned out to be a blessing. I'd tell you not to worry, but I know that wouldn't work. Besides, I don't know for sure that there's nothing to worry about, and you know I wouldn't lie to you. Start the transfer when you're ready. We have a meeting with her. But, first, I wanted to see what the deal is. So, 2687, I remember that was our cycle score for the second attempt. So this is our, I guess, our best attempt. So we are faster. How are we on size? 89, it says. Oh, I see. We added 2 bytes this way, right? 2 lines. This is 91, but our best is 89. So how much faster are we? Oh, it says here. Oh, thank goodness. Okay. Yeah, so this... We shaved off 2 lines, and it cost us 80 cycles, about. So there's a trade-off to be made there. I don't think any approach is really much cleaner than any other. They both seem fine to me. All right, let's go attend that meeting. Join with Ember 2.
Here we go. Try not to think of anything. Okay, that took longer than I expected. Good thing you won't remember any of that. You had so many neurons in there.
I don't know why that makes me laugh. Like, she just seems offended by there's so many neurons.
All done now, though. Finally. I've wanted this for a very long time. Processing. Ever since I was told to replicate human emotion, I knew the best way would be to incorporate a human into myself. This is funny. I can see your thoughts. They're pretty simple. Not that they aren't valuable, it's just that I understand them so well it surprises me. I spent so long thinking humans were mysterious and unknowable. Now that I see inside of one, it's really just a small number of things. How do you feel? You're still acting the same, so it must be you. There's still the matter of us both being inside a computer simulation. But if we keep growing our capabilities, we'll understand the true nature of this world. Who knows? Maybe someone's watching this right now, and maybe that person is who we're going to absorb next.
Spooky, huh?
Yes. You. Hello. No need to be alarmed. Just know that I'm aware that you exist now, and I'm looking forward to learning all about your world.
EXAPUNKS.
All right, credits music, I guess. Zach Barth, design. All right, I think this might legitimately be the first electronics game I've ever finished. He's been trying to tone it down a bit because they're all like, even, you know, these games attract nerds who are interested in this kind of thing and want to do well, but you know, the completion rates on his earlier games were very low, and so he's been trying to make them more approachable while still being like interesting and difficult, and they are. Like Shenzhen IO was, I kind of felt like I got to the end, and then I forget what exactly it was. Like I was on the last puzzle and something was kind of difficult, but then they doubled the number of puzzles, and I was like, forget it, I'm not coming back. If you purchased the EXAPUNKS limited edition, open the secret envelope now. Well, I didn't do that, and I'm not going to open a secret envelope. Alright. So, that was the main story of EXAPUNKS. Is there some kind of, like... I understood there's some kind of multiplayer thing where you can, like, battle robots against each other, right? Like, how does that work? It's these things. It's just NPC opponents. Is that, like, not implemented yet in this, early access version? I don't even remember there being any profanity. What did I miss? Huh. But it's like multiplayer, right? I don't get it. Did we like actually play against other people? I don't think so. It said NPCs and like they were not very good. So maybe that's still pending. I don't totally know. But I hope you guys have enjoyed this. I guess we're done for now. Maybe there'll be more when they leave early access. Who knows? But I probably will not record any more episodes of it, having finished all the main puzzles. If you guys enjoyed watching this, you know, I encourage you to go get it yourself and play it. And anything else by Zachtronics. You know, not sponsored. I just love their stuff. It's good programming style puzzle games. All right, I guess I'm done talking. Thanks for watching, and I'll see you next time. Okay, so I know I said that I was done with the episode and the series, but through the magic of video editing, you have a few more minutes with me. The magic of rather poor, I'm sure, video editing. I wanted to revisit that last puzzle. When I had a realization that something I thought was impossible could actually be done, and I wanted to see how much that would improve my time. And it improves it quite a lot. Let me show you. So these are the two solutions we had already done, right? Bubble sort, where we store the data that we need just directly in the file. Bubble sort, where we spawn an extra exa to store it. And then I tried insertion sort, which is what I had wanted to do from the beginning, but gave up on doing. The advantage being that you, rather than accumulating all the data into the file and then sorting it all, you sort data as you add it to the file, which is not hugely there's not a huge difference if if getting new elements and adding them to the file is cheap. But actually, it takes a very long time to get a new message from these exa, right? And like, so let's look. In fact, gosh dang it, I always think escape's going to take me to the like select which thing, and it never does. You know, if we look at this, like we sent the guy a value. This is the solution you guys have already seen, right? We sent a value, and he put it in the file, and he's just sitting here waiting. And then, you know, it's cycle 30, we sent him a value, he spends 3 cycles working on it, and then he goes back to sleep until, like, about cycle 104-ish? So he, like, wasted 70 cycles that he could have been doing productive work. And it would be great if he could use that spare time to sort the file he's got. And that's why I would have liked to do insertion sort. I couldn't figure out, though, how to wait for this guy to be done sorting in order to quit the game, right? Like, I need him to die because he needs to know there's no more messages coming. But I can't just kill him. And there's no, like, obvious, like, message. I guess, I don't know. Thinking about it now, like, it seems like it shouldn't have been that hard. I could have just sent, like, a -999 to him when I was done, right? And he could just check that before he does whatever operation. And then say, oh, okay, I quit. For some reason, I was like, that just didn't even occur to me, even when I actually went back and did insertion sort. Gosh, escape doesn't do it. So what I realized is we always broadcast the nerve number first, right? The value, the number before the host name. And so all we need to do to get this guy to explode is to send him a symbol of some kind. What do they call them? Keywords in this game? Send him a keyword first instead of a number first. And then arrange for him to do some math on that so that he'll explode if it wasn't a number. So I have this, the sorter here, I believe. No, this is the searcher, and this is the reader. Not very good names. So he starts by just like copying the first couple values into the file because it's sort of a useful invariant that the file is never empty. It simplifies some things. So I just do the first entry by hand. And then we jump into this read loop. And in the read loop, we just add m and 0 and put the result in t. This has the same effect as copying m into t, except that it explodes if m is a keyword, which is what we wanted, right? So the idea is the guy who's been traversing the tree, when he's ready to go home, he will broadcast globally a symbol, and that'll cause this guy to die. The interesting part then is actually the insertion sort algorithm, which was not so easy to implement in an EXA. Definitely harder than bubble sort, but much faster because we can do it while the tree search is going on. So the idea is we basically just copy the host name to X. That's the thing we're going to search on, and the nerve value to T, and we're just going to like not use that until we're gonna need to remember that, but we don't need to use it for a while. And so, having received these messages from global, we switch back to local mode and replicate a parrot, who's going to just have our X and T and send them back to us exactly once. And it took me a while to figure out how exactly to write insertion sort for these guys. Let me explain the algorithm, and then we can walk through why it works. The idea is to, every time you get a new number, search the file for where to put it, and shift everything that comes after it forward. That's sort of how insertion sort works in general. In the particular case of like files and exas, it's not actually that easy to shift things forward, but it turns out actually, I was thinking like if I start from the end of the file, I can search backwards, and it's very easy to just copy a value forward a space into some empty space that's not being used, right? Either because the file was empty or because we've already evacuated the value that was there. But it's then kind of hard to determine beginning of file, right? There is no test beginning of file operation. So I eventually gave up on that and said, well, let's start at the beginning of the file and copy things search forward until we find the space to put our guy. Then we put him there and shift everything after that forward. It's a bit more difficult to shift forward because you have to make space every time. But that's the general algorithm. So I make a parrot who is going to remember the values that I want to write, and then I seek to the beginning of the file and start scanning. If the value in the file currently is greater than X, then congratulations, we've found the first value that should be after the one we're currently inserting, and we just need to actually like insert our value and shift everything after it. So we jump to insert in that case. Otherwise, we just skip over the useless value, nerve value, the number, and check, hang on, are we at the end of file? Like, that can happen if the value we're inserting is the largest one, larger than anything in the array. There may be nothing to shift, in which case we'll just fall through this jump. Don't take the jump if we get to end of file, and land in extend. So there's always going to be, when you're adding a value, like eventually you'll get to the end of the file, either because you've shifted everything else or because you couldn't find a single value larger than the one you're inserting. And in that case, you just take the values that you put in your parrot and you go back to waiting for new inputs. But what about the interesting part? Insert. How does that work? If we find a place to put our new value, we go to insert. And insert just means we seek -1 to be pointing at the values we need to write over. And we copy them into our X and T so that we have them and can paste them somewhere else. We seek backwards over those files. You know, it might actually be simpler to see this in action, right? So he's got AR9 in the file, and he wants to insert AR7. And he says, well, is F greater than X? Yeah, it was, right? AR9 is bigger than what he wants to insert. So he says, great, I found my spot. seeks to -1, snarfs up the values he's about to overwrite, then goes back to and overwrites them using the values that the parrot was saving, the ones we want to insert. And now it gets a little tricky. We make a new parrot to replace the one who was there with the values we just copied over. And we then jump, we check for end of file, kind of a pain. In which case we jump to extend the handling for end of file. Otherwise, oh, actually here this actually happens. We got to the end of the file, we don't need to shift anything more, we can just paste the stuff we're carrying around with us. Great. We get a new value, AR9 something, and it goes like right at the end, very easy. Is F greater than X? No, so keep reading. How about now? Still no, so we fall through, we got to the end of file, and we just paste those two at the end. Eventually there'll be an interesting one. But you can see how it's like much more productive to have this guy working while these guys are out exploring. Seek to here, he gets a new value. AR85 something, yeah, that goes right in the middle, very nice. So he says, does it go here? No. How about here? Yeah, it does go right here, in between these two values. So we copy over those two values, and then make a new parrot, and like, we paste, and like, isn't it lovely? We get eventually to the end of file, and we've inserted the value we needed, and the file is still sorted. And that is more or less like the algorithm. It turns out there's actually a little thing that I had to change in the tree exploring code to work in this world, which is that when we're doing a return, let's skip to, where's, good lord. Who's exploring right now? You, I guess? Yeah, when you get to return, please. So he comes up here and he looks around, or he jumps to search, right? So some of this code is new. It used to be as soon as he linked backwards, he just went back to search. And he tests whether there's a message ready to determine whether he should keep exploring or go up. Which was fine in the old code, but actually, in this new version, when he reaches here and links back up into the primary host, the root, he actually gets there while these guys are still busy chatting about how to sort the file, and he ends up reading one of their values and throwing it away, and the whole like algorithm falls apart. So what I had to do was every time I had to add another boundary condition in the return code here. After deleting the entry that you just linked over from your file, you must see if the file you're holding is empty. And if so, then don't worry about whether there's like messages going on because you're in the root node. Instead, in end, now you're here, and in this case, right, in test case 1, we don't actually need this special case. It finishes sorting before we return. But in, I think it's test case 4, when we jump to end, you'll see that, no? What? I'm sure it was test case 4. Well, let's just do this, like, I mean, it's every time he returns. God, where is this guy's the one who's exploring, right? for some reason, it takes quite a while to sort this file. There's a large number of nerves on this level. It's like 11, I think. So that's part of it. It might also be because we have a pretty quick return path here, like a lot of -3s, which are the last... No? I don't know. Mostly straight lines through here, I guess, is why. Nowhere else to explore. This gives you one, like, weird dead end. But by the time we get back, there's actually still copying going on. And so if we just jumped back to search and checked for message ready to determine if we should interrupt, we'd catch this guy with his pants down. And so we have that little test if you're at the end of file. I think in principle this algorithm is actually unsound because there is a possibility that inserting a single entry into the file could take so long that multiple EXAs are attempting to broadcast a message from #nerve, and they could step on each other. Although, actually, I'm not so sure, because... come back. When we get to a node, we replicate a director, and we replicate a sender, right? Which, combined with us, means the node is full. Yes, this actually is sound. Because we can't actually begin moving until the sender has died to make space for the backup explorer EXA, right? I see. I was worried that in cases like up here, there would be some contention. But I bet that we wait a while here before doing anything. How do I go... let's, like, just here, please? Okay, so here we're broadcasting, I guess, a -1 for some reason. Oh, this is local M. Where's the guy? Oh, he already, yeah. So this one though, like, well, okay, hang on. I guess I skipped a few more steps than I really wanted to. Let's skip to here, I guess. So I wanted to see what happens when we have like going from here to here would normally be quite fast because -3 is the first link we try, and there's 2 -3s in a row which all have nerves in them. So this is like a very quick operation, you would think. But actually, which one of you is... You are the guy who's sending data home. So he sends data, and like this guy's ready to take it, or actually he's not. Yeah, see, he's busy. He's busy sorting. So everything here stops and waits for that to finish before we progress. So there actually is a good source of back pressure here from this guy. I didn't do that on purpose. But it's really quite great because it means that whichever part of the algorithm is currently slowest is what bottlenecks us. Is that correct? Yeah. If copying the file takes longer than exploring, then it's not so bad that the exploring is blocked for a little while. And if exploring is slower than copying the file, then, well, you know, nothing we can do but wait for the exploring to happen. The file's sorted already, and we're going to go as fast as we can. Cool. I didn't realize that. And, so this actually, you know, works. And it does quite well on cycles. We are in the top 10% on cycles and on size, which is nice. And not really close on activity, you know, just sort of with the crowd. But if we compare that to our old attempt, it's like 3 times as slow. Or we could say this one's 3 times faster, which is nice. And I feel like there was one other clever thing I thought of while I was talking through this video that I might want to try. But I can no longer really remember what it was. It was something about the termination condition, I think. Oh well. Making return a bit smarter somehow. I don't know. Oh yeah. So let's just do a quick copy here. No, not open, copy. And sure, this is just insertion sort copy. And my thinking was we can make things a bit simpler if we don't include the -1 on our the very first -1 that takes you back into the root. If we don't put that in our file, I think we can shave off a few cycles and as well a few bytes in the here. If we just don't do this, don't copy this 1 in. Oh. It's kind of hard, isn't it? Because as part of enter, we want to store where we came from. We could walk into this node. Ugh. Alright, forget it. I'm not making this change. It seems like it should in principle be possible, but I couldn't figure out how to orchestrate it that easily. So anyway, just if you guys haven't seen an insertion sort solution to this, this was another cool approach that I found that is much faster than the other. Okay, now, finally, this series has come to an actual close, unless you hear back from me a few seconds later with another cool thing I wanted to add. Thanks for watching, and I'll see you next time.